In this video, we're going to talk about Claisen and Dieckmann condensations. So in Claisen condensation, an ester is going to react with another ester to form a beta keto ester. And in the first step, we're going to have to use a strong base, such as hydroxide, preferably hydroxide. And in the second step, we're going to have to acidify the solution. So what is happening here is that it's very similar to an aldyl reaction. In the first step, the strong base, hydroxide, the base has to match the ester. We'll get into that, why that is in a moment. But the base, the hydroxide is going to come in and depronate the alpha carbon. And it is going to give us an enolate ion, which is resonance stabilized. And just like in an aldyl reaction, our enolate ion is going to attack the carbonyl-carbon of another ester. And this is going to cause the double bond to break, and we're going to form a new bond, like so. As you can see, let's number the carbons. We're going to, this is carbon 1, in response to that carbon 1, carbon 2, carbon 3, and this is carbon 1, carbon 2, carbon 3, there. As you can see, the new bond that is formed is right there. So, in the next step of this reaction, the tetrahedrocarbonyl addition compound is going to break down, and it's going to kick out the ethoxide ion. So this is going to give us a new double bond, our double bond back, and eject the ethoxide ion. And this will give us our ethoxide ion back. So, because this, if you look at this beta keto ester, the alpha hydrogen here is very acidic due to the stabilization by these two carbonyl groups. So this beta keto ester actually has a pKa of 10.7, but the starting ester that we have only has a pKa about 20 or so. It's a pKa of 22. And because of that, the ethoxide ion is going to come in and depronate that alpha hydrogen and give us a ion and ethanol. And so in order to get our product, then we have to do the last step and acidify the solution, acidify the reaction. We can use a weak acid such as HCl in water, and that will simply give us our proton back. And we will end up with a beta keto ester. So when you're doing a Claisen condensation reaction, we have to use the correct base that correspond to the ester. So in this case, we would have to use ethoxide. And if it was a methyl ester, we would have to use methoxide. The reason for that is if we were to use OH for this, so what would happen if you use hydroxide for this is that hydroxide can come in and it can attack the carbon there, and it can form a tetrahedral addition compound. And this is going to cause the collapse of that tetrahedral addition compound, and it's going to kick out the ethoxide. And it will give us a different molecule. It will give us a carboxylic acid. And this carboxylic acid, under basic conditions, is going to be deprotonated into a carboxylate ion. Now, instead of OH, we were to use another different base, such as methoxide. If we were to use methoxide, something similar would happen. It's going to give us a different ester. The methoxide is going to come in and attack the carbon, similarly to how hydroxide would, and it will form a tetrahedral addition compound again. And this will cause the compound to collapse and kick out the ethoxide, and it will give us a different ester, and and so this will become a transesterification. Under these conditions, though, the Claisen condensation can still occur because this is a reversible reaction. This, because we kicked out the ethoxide, this ethoxide can come back in and kick out the methoxide instead, giving us back our starting material. However, the condensation will have, if we were to proceed with Claisen condensation, under these conditions, we're going to get two different products, one with methoxide with a methyl ester and one with a ethyl ester. So if we were to proceed with Claisen condensation in these conditions, it will give us something that looks like this. Now let's talk about Dieckmann condensations. Dieckmann condensations are basically just intermolecular Claisen condensations. So if we were to have a 3, 4, 5. It's very similar to intermolecular autoreactions. And if we were to react this with and it's going to give us a 5 or 6 membered ring, and in this case it's going to be a 5 membered ring. The mechanism for this reaction is the exact same as a Claisen condensation reaction. What is going on is that the ethoxide is going to come in and deprotonate the alpha hydrogen. So it can either deprotonate that alpha hydrogen carbon or that alpha carbon. Since this molecule is symmetrical, it doesn't really matter which one. And this is going to create a enolate ion. And this enolate ion is going to attack the carbonyl-carbon of this functional group on the opposite side, and it's going to cause ring closure 1, 2, 3, 4, 5, and form a 5-membered ring. See, so this would be carbon 1, and this would be carbon 2, 3, 4, and 5, if we were to use the numbering here. So now let's talk about cross-claisen condensations. So in a cross-claisen condensation, there's going to be 2 different esters that will come together and form our product. So similar to cross-aldo reactions, there is a problem of many possible products. So if we call this reactant 1 and call this reactant 2, 1 can react with itself and 1 can react with 2. 2 can react with itself and 2 can react with 1. So we're going to actually get 4 different products here if we were to do this exact reaction as shown. So when reactant 1 reacts with reactant 2, it's going to form a product that will look like this. And when reactant 2 reacts with reactant 1, depends on whose alpha carbon you deprotonate. So in this case, the first one, we're going to deprotonate their alpha carbon. It's going to form a product that looks like this. And if reactant 1 were to react with itself, it's going to form a product that looks like so. And if reactant 2 were to react with itself, it will form a product that looks like so. Now, as you can see, there's 4 products that we can get from this. So if we do this, proceed this with the classic Claisen condensation, this is not very synthetically useful due to how many byproducts that it can give us. Let's talk about ways that we can, if we want the products of, say, reagent 1 and reagent 2, if we want this product as the major product. What we can do is that we can use either a different reactants. So if we were to use reactants with no alpha hydrogens, that can be deprotonated, and they can only function as inalate anion acceptors. That will eliminate some byproducts. So some chemicals that could be like that is, say, ethyl formate. This was a hydrogen, and this has no alpha hydrogens that you can deprotonate. And something like ethyl benzylate. This also has no alpha hydrogens that you can deprotonate, and they can only function as inalate anion acceptors. Now, there's another way that you can prevent other byproducts, although it's still not 100% yield. If you want, say, if you don't want to use something like a change your reactants, perhaps, you can use something like LDA. So if we want the product of 1 and 2 as a major product, what we can do is that instead of immediately reacting 1 with 2 with ethoxide, what we can do is use a very strong base like LDA, and this LDA will actually deprotonate basically all of the reactants into inalate ions. And if you are used to use 1 mole equivalent, so it's important that you use 1 mole of LDA per 1 mole of reactant. In this case, it would be 1 mole of each. So this will deprotonate basically all of the starting material. And the reason why we can't use something like ethoxide is that it will only deprotonate some of it, and some of them will be left over as the starting material. And now, once that we have this material, LDA looks like this, by the way. And this will attack this alpha hydrogen and deprotonate it. And in this reaction, all of the LDA will be consumed. Once we have this, we can react it with our other starting material, which is this. And this will form our desired product as a major product. However, this is still not 100% yield. There are side reactions that can occur, but this will give us our desired product as the major product. Next, let's talk about the hydrolysis and decarboxylation of our products, beta keto esters. If we were to, let's not pay attention to these two. Let's say we have these two reactants that we got from a reaction of 1 and 2 and 2 and 1. So what we can do is that if we were to add H3O plus, well, in a laboratory setting, you'll probably see that saponification first, that it'll just simply produce a better yield. If we were to add H3O plus, it is going to convert this into a carboxylic acid. So the ester group will be converted to a carboxylic acid group. And same thing with the other product. The ester group will be converted to a carboxylic acid group. Now, what you can do at this step is heat both of these products, and they will undergo decarboxylation, where they will remove the carboxyl group, the carboxylic acid group, sorry. And we're going to be left with these two products. And as you can see, these two products are isomers, and that's also another way you can get to the same product from two different products. It's through hydrolysis and decarboxylation of beta keto esters, and this will yield us two of the two symmetrical ketones.